Maybe we can resume, please. So, welcome to the final session of today's of the workshop today. So we're honored to have our speaker, Professor Christian Robert, who's a professor at Paris Dauphine and at the University of Warwick in the UK. Some of you may or may not know or should know that Christian is very well known for his work in Bayesian statistics and Bayesian computation. And amongst some of his achievements are being a former president of ISBA, a member of the research section of the Royal Statistical Society. He's a former editor of the Journal of the Royal Statistical Society, Series B. He's the current co-editor of Biometrica. He's published more than 200 articles and a dozen books, and has more than 40,000 citations, which is quite an achievement in statistics. And he's going to be speaking on how many mixture components. So please take it away, and thank you for coming, Christian.
Thank you, AJ. Thank you very much for the invitation. It's a great opportunity to visit KAUST and meet new people. What I want to discuss today are some most recent results on mixture estimation from a Bayesian perspective and computation from Monte Carlo and MCMC perspectives. This is joint work with Adrien Hérault, who is a PhD candidate completing tomorrow, and Judith Rousseau, with a colleague at Dauphine and Oxford. So, I mean, the title changed a little bit, but the spirit, of course, doesn't change so much. But before starting on the outline of the talk, I just want to advertise for positions that we have in Paris or Warwick for both PhD students and postdocs, thanks to the funding of a new ERC grant that we received with Eric Moulin, Gareth Roberts, and Michael Jordan. So in case you know of candidates, just contact me or the other PIs of the grant. Okay, so yeah, there will be pictures that are mostly unrelated with the talk, just to put some color in the slide. So as a coincidence, 2 weeks ago, there was a celebration of Sylvia Richardson's career in Cambridge. She's retiring from the MRC unit at Cambridge. And so I was invited to participate. And I gave some bits of this presentation because for me, she contributed very seriously to the analysis, the Bayesian analysis of mixtures, and in particular to the problem of estimating the number of components through this JRSSB red paper from 97, using this then novel technique of reversible jump MCMC, which both Sylvia and Peter argued as being one way of going through an unknown number of components. Sort of paradoxically, I have not covered the comparison with reversible jump MCMC for computational problem I may mention later. Okay, so a bit just unfitting, but what are mixtures of distributions? They are simply a convex combination of other densities, and those other densities are themselves parametrized. So that's one family of probability densities among other, and what make them special is this combination of densities and weights that turn the statistical problem, especially in a computational way, a bit more of a challenge. And I've been interested in mixtures from the very early days of my career, starting in 80. Actually, I was working on mixtures when I was in the army in 87. Separating, I didn't stay long in the army because it was a French compulsory service, but they had me analyzing multiple source separation, and so that's when I met mixtures. Anyway, so I mean, if you're following a Bayesian, maybe I'll turn that into a smaller size so that it fits here. So when you're doing a Bayesian analysis of mixtures, there is one question that is to specify the prior distribution on all the parameters involved in the distribution. And that's a bit of a challenge given the partial identifiability of the parameters. So you have to be somewhat careful in specifying the prior distribution. And so with Clara Gradzian, a few years ago, we had studied the default prior selection in mixtures by returning to the fundamental Bayesian principles for the construction of priors, namely Jeffreys priors. And Jeffreys priors are defined through the information matrix that comes with a mixture or any distribution as the square root of the determinant of this information matrix. And this led to interesting questions, both numerically and statistically. So we tried this approach for Gaussian mixtures, for instance, and this turned into a real challenge for which we found some partial computational solution. I will not mention here, but something like delayed acceptance MCMC was one approach. But this ended up with some equations that were hard to solve, namely that if you use such a prior, so it's a measure with infinite mass, and the fact that you multiply by your likelihood that is only partly identified leads to a possibility of an improper posterior, something that doesn't exist. Therefore, you cannot do Bayesian analysis in that case. And I mean, looking at the black box formula, you cannot give an answer. And unfortunately, looking at MCMC run, this is a long-going issue, that if you're running MCMC on a target that is a measure and not a probability density, doing Gibbs sampling, for instance, it's not necessary that your Markov chain will tell you that something is wrong. You may just see a stable behavior, and the output is not telling you the full story. So there are published papers, especially in the early days of Gibbs sampling, where actually they were dealing with an improper posterior and no one realized it, and it got published. And so this was a difficulty. So I mean, we went through another form of priors in that context, at least for location scale mixtures. So when all terms in the mixture, all densities have parameters that are location and scale. So I mean, the simpler example is made of normal distributions, but could be any other type of location scale density. And I mean, something that works out rather nicely is to reparameterize all components in terms of a common location mu and a common variance sigma. And I mean, so sigma is the variance of the entire mixture, and mu is the mean of the entire mixture. And it's funny because it's about maybe 20 years earlier, no, sorry, 30 years earlier. We had tried this approach with Kerry Magnuson, but without imposing that mu and sigma were global mean and global variance. And we are not able to deal with this improper posterior issue. If instead you impose for mu and sigma squared to be the mean and the variance, this turns all the other parameters into members of or elements of a compact set. And thanks to that, you have only two parameters that vary all over the space. This means that priors like pi of mu sigma equal 1 over sigma, which is an improper prior, delivers a proper posterior with only two observations, provided you use, for instance, a uniform distribution on the compact set. And so there is this, it sounds like a very cheap trick, but it works to define a reference prior in a fairly general setting, no matter what the number of components, thanks to this compact constraint on the other parameters, including the variances, which is really the main issue. Now, what are the computational problems or inferential problems that come with mixture? The most important one is this non-identifiability of components, namely that because the object is a sum, no matter which order you write this object in, return the same density. And so you cannot identify one component in particular, it's only the sum that is identified. And so this is both irrelevant and very important. Irrelevant because the density structure doesn't require components to be identified, and very important because this creates a lot of mode on the likelihood surface. So no matter what the number of observations, there will be an order of k factorial modes on the surface. And the more observations, the pickier this mode. And so visiting the likelihood surface or the posterior surface is going to meet with this difficulty. And if you don't pay attention, and we'll see very quickly an example where this becomes a numerical issue for inference. So again, this is not at all a new problem. AJ worked on it in its early stages. And there were different proposals to try to overcome that with more or less a strong computing requirement. And this will permeate all the issues I will mention later. So there is this switching problem of visiting all the modes, namely that, and this is again a screen copy of the Richardson and Green 97 paper. If you don't pay attention to that, you may end up with Markov chains that are stuck in one of the modes. And of course, this is a bad quality copy, but a regular MCMC would have difficulties to move from one mode to the other for this parameter mu2 that is a mean of one of the normal components. Well, if you let, and this was the argument of Richardson and Green, if you let the number of components vary and only record the episodes where a certain number of components is the current proposal, say k equals 3, by eliminating and adding components, the meaning of the different terms is totally blurred, and there is this sort of behavior of jumping between the two modes of this example. So at least at the shuffling approach, this embedding of a fixed number of components mixture into a variable number of component mixture creates the exploration or the bridges between the mode to avoid being stuck at one mode. So it solves the label switching in one way, but by creating a space that is a layer or a pile of layers of different models. So it has added complexity. Now, there are ways to try to avoid that difficulty by looking at objects that do not depend on the labeling. And again, we'll come back to that in a minute. For instance, in a paper that we wrote about this issue from an MCMC perspective quite a while ago, we focused on predicting labels of the missing variables. And this only consider pairwise associations that do not consider what is component 1, component 2, and so on. So this clustering approach is insensitive to label switching. Now, to complete this short introduction, another difficulty that comes with mixtures is how to compare models, so to compare 3-component versus 7 or 26 versus 200. There is a theoretical corpus of work that justifies the use of the base factor, which is the ratio of the marginal likelihood for a finite number of components, and to some extent, in some cases, for even an infinite number of components. That is, there is a Bayesian theory of model comparison that extends to non-parametric models. Despite having an infinite number of parameters, you can compare those models through the base factors, and they are consistent in the sense that if you are in one model, the base factor will converge in favor of that model, will converge to infinity. So eventually, with probability 1, we'll select the proper model. And actually, with Adrien and Judith, we reconsider this problem here, and under some assumptions that I will not really detail, we showed that the base factor comparing a finite mixture and a Dirichlet process mixture that I will detail later is converging in that sense of the picture, that if I increase the number of observations, the base factor goes, the log base factors goes over 1 in favor of the right model, whether the data is from a finite mixture or from not a finite mixture, which is asymptotically covered by a Dirichlet process representation. So, I mean, that's what we mean by the consistency. If you oppose this finite mixture object to a Dirichlet process mixture that, again, I will detail, the MDP is the marginal likelihood, and when the data is from a finite mixture, this marginal likelihood for the alternative model is going down at this speed with a guarantee that we additionally cover the right density of the data. Okay, and there are assumptions that are hidden under the carpet that guarantees that, I mean, the ratio of the marginal goes to infinity in favor of the right model. Okay, now I will focus in the rest of the talk on the numerical aspects of computing this evidence, the base factor being my marketing item for considering the evidence. So the evidence is the marginal likelihood. It is the integral of the likelihood times the prior. And if you have a collection of models indexed by k, you can compute mk for each family. That gives you a numerical indication that your model is suitable for your data, or that your data is compatible with the model. And so this mk, this marginal or evidence for model k, is crucial for Bayesian model comparison. And there are a lot of approaches to return an efficient approximation to this mk. One that is quite appealing is due to Chib, or one version is due to Chib. There is other versions found in the literature, like Julian Bizags had an unpublished version in 89, which is based on Bayes' theorem, namely that the marginal of x is a joint of x and theta divided by the conditional of theta given x. And so if you want to know the left-hand term, you just have to compute the right-hand term. except that it's not available due to the fact that this denominator is not available. You know the numerator, but the denominator cannot be computed exactly, otherwise you will know m k of x. And so what Chib proposed was that if you could find an efficient estimator of the posterior distribution of the posterior density and plug it into this ratio, then you would get, by proxy, an estimator of m hat x. Given that this base formula has a nice property that the left-hand term doesn't depend on theta, so on the right-hand term, you can pick whatever value of theta you wish. For instance, the most likely value of the parameter or any form of convergent estimator. So all that remains is to build an efficient approximation to this density. And in a class of models where you use auxiliary variables that are also called latent variables, you have an unbiased estimator of the distribution of theta given x as the average of the conditional distribution of theta given x and z. And in the context of latent variable models, such as mixtures, you do have these structures that you can exploit, namely that in the simulation of the standard Gibbs sampler, you do produce not only simulations of the parameter, but of the latent variables or the auxiliary variables. It's a product or byproduct of the estimation. And on top of that, this density is fully known, including normalizing constant. So you can write this estimator, and not only it's converging, but it's converging at a parametric speed. So you're estimating your density at a parametric speed. It goes down. I mean, the error goes down as root t, not a weaker power of t, as in non-parametric approach. So this is a very good estimator that you compute easily and quickly. So where is the caveat in using this approach? Well, it's level switching again, because z, the vector of z, is made of indices of the different components of the mixture. And due to this multimodality, given that component one means nothing in the sum, if the Markov chain produced by the Gibbs sampler doesn't explore all the modes, Z will also consider only one of the modes of the mixture. So as an object of interest, this could be an issue, and it is an issue, as we will see in one example. Let's go that first. That is illustrated on this most classical benchmark of galaxy Reynolds speed that has been used for quite a while. There are 82 galaxies. The number of components is unknown. It's a bit of a benchmark, so maybe it's not so relevant, the physics behind. You are using some priors, standard priors on the Gaussian parameter, and then you compute the evidence using Chib's estimate. And so, for instance, if you take k equals 3, the log evidence is minus 105. Now, this is using the output of a regular Gibbs sampler that doesn't see a lot of permutations between the modes. It gets really centered on one of the modes. If you impose a permutation by an average of all the possible permutations, you get a log evidence of minus 103. And actually, in that case, it's exactly the log of factorial 3, which means that you're really exploring only one of the 6 modes in the picture, and the difference is telling you that by not label switching, you are missing the correct value of the evidence. And so if instead you average across all permutation, you get a different ordering of the log evidences that turn in favor of k equal 5, for instance. But again, that's more of a term than a realistic problem. So because of this lack of switching between modes, a solution is to Chib's problem, or to the problem with Chib estimator, is to also average across all permutation of the indices to recover the predicted symmetry between all those modes. Because you know from the beginning that due to the sum representation of the mixture, you should have perfect symmetry between the groups. In other words, the marginal distribution on the first component parameters marginally is exactly the same as the marginal on the third component, because again, first and third mean nothing in the sum. And so since you must have symmetry, you can impose symmetry by averaging the original Chib's estimator across all permutations, which does recover this table I had just presented. Now, to give another snapshot of the 97 paper, they produced another estimation of the evidence, which they turn into a Poisson distribution on the number of parameters, but of components. That's irrelevant. That by nature avoided as well the label switching, or reproduced perfectly the label switching, to be more precise, at the cost of visiting a lot of models and rejecting a lot of moves. So, I mean, reversible jump MCMC is a great concept. I mean, it's beautifully validated by a construct of symmetry between the move, which is why it's called reversible jump. However, practically, it has very low efficiency by rejecting a lot of the proposals, because you had to guess projection in different spaces that do not always achieve interesting points in the other spaces. So here you may get acceptance rates of, well, it's there written here. And for galaxies, I managed to get up to 18%. But I had experience in hidden Markov models where the acceptance rate was 0.02, I mean, 2% of the proposal. And so once you start doing that, if you have a lot of models to explore, you see, you spend a lot of time going through them. Now, something that comes out of this reflection on evidence is that if we can remove the reason for label switching, which is the identification of each component differently from the others, which creates this modality, this multimodality that simulation method is bumping into, we could do better. And actually what happens is returning to this loss function slide I presented earlier, namely that if you look at the clusters that come with the mixture estimation, or the partition of the data into groups, those groups are attached to actual data. And so they just tell you that those two data points are likely to be in the same cluster, which means that they are likely to come from the same component of the mixture. But they don't give a number to the clusters. This is just a cluster of observations 3, 10, and 25. And what happens in nice situations where you have exponential families for the components and exponential families for your priors is that you can integrate out the parameters to reapply Chib's formula, but to the clusters rather than to the parameters. So this is the same base formula, but for the pair XC rather than for the pair X theta. And well, here is the illustration on the prior on the partition that comes from a Dirichlet prior on the weights. It involves the data only through this number K plus, which is a number of clusters that are filled with some observations. So the number of non-empty clusters. And so if you can integrate out the parameters thanks to conjugacy, you have an easily computed marginal distribution of X given the clusters. There is absolutely no label switching, and the computation goes much faster with efficiency in this approximation of the evidence. So that's one of the solutions. Another one we are going to examine is starting with bridge sampling. The bridge sampling is a multiple important sampling where you're using instead of one proposal, several proposals, and you stabilize your estimator by pretending that your different samples are coming from a mixture. That's one way of explaining bridge sampling. And so, I mean, the evidence approximation in this situation is that you have two types of samples, one from Q, one from pi, just as in regular important sampling. But instead of weighting the theta n by pi over Q and the other one by Q over pi, you weight both of them by 1 over the mixture of the two importance functions that you have used, and this stabilizes quite a lot the estimation by reducing the variance in most situations. And when Q is free, you have the problem of selecting the optimal Q. And so in the case of a mixture problem, you can use partial conditionals to create another probable distribution that you can write down explicitly. There are a lot of symbols, but lambda, the weights, and the size are the other parameters. And essentially all those terms are available and easy to simulate from by a kind of cascade sampling. So that's one of the solutions. Of course, again, if there is no label switching, and you should have label switching, you can average over all the permutations. Yeah, I think I'll skip that in the interest of time. I mean, the elephant in the room is obviously that averaging over all permutations quickly becomes unfeasible, and therefore you should sample the permutations in order to reduce the computing time or to achieve a manageable computing time. And so we explored a bit that direction with Kate Lee a few years ago. So this was the idea, and reducing the computing effort to some extent. Okay, a word about a different approach using sequential Monte Carlo. Structures like mixtures are easily manageable by sequential Monte Carlo, either regular one by looking at the likelihood or specific ones by looking only at subsamples that you progressively increase all the way to the sample. So if you create a sequence of targets that start from the prior distribution and end up with a posterior, so it's an increasing sequence of temperature or powers lambda I, and you move a set of simulations from one target to the next by some form of regeneration. I mean, this is really a typical SMC setting. You have a transition kernel, you reweight them, and then when the sample degenerates, you resample as traditional. Then, as a byproduct, without any effort, using the renormalizing constant on the weight, you get an approximation of the evidence. So that's a really good argument for SMC, namely that it returns as a byproduct at no cost this approximation of the evidence. And then you have the choice of the transition in the sequence that you can pick this way, for instance, using the full conditional of the different zeta. So again, we're using this pseudo posterior exploiting the full conditional. And the importance weight can be easily returned. Now, what does that produce? It's a bit of a dense comparison, but I'll take that one because it's not as high as the others. This is the evidence that is produced by fairly intensive, purely numerical integration. What I mean that as the number of components increases, Chib is getting worse and worse because of this lack of exploration of all the modes. So this is a log evidence. It's getting away more and more away from the correct value, both by creating a bias and by adding more variability. If you use an average or permutations, again, we are missing some permutation, and so we are also leaving the right value. Those that resist the best to the increase in K are the first SMC solution and the second one produce that is, quite efficient, as you can see. Using the partition as some worse in the sense that it resists, despite having more variability, it does resist to the increase in K. And for some surprising reason, simulating for the prior remains a solution here because it's kind of almost free, so you don't have time, you don't spend time constructing the estimator. And this is a bit of a side remark. And in terms of computing time, they're using exactly the machine time to produce those estimators as computing time increases. You can see the clear difference using sampling, important sampling, that means the last solution. This is a Chib alternative, which does resist the comparison, but definitely this one is much faster. Okay, so these are mostly empirical conclusions. We don't have theoretical result to tell that one speed is better than another, but across simulations, we found that bridge sampling doesn't resist well with the sample size, and some of the methods cannot face a large number of components. The last two are, the last one is definitely doing better. Okay, so another direction we considered in this work with Adrien and Judith is distributed computation. And again, there is a clear connection with the recent paper of Alexander Bisholz, Daniel Fouque, and Sylvia. They got published just last year. So the notion is that if you have different groups of data points that are groups for different reasons, storage or maybe privacy, how do you handle the construction of the evidence? You cannot merge all the data sets together. In that case, the posterior is always the same. It's the product of the likelihood times the prior, which, if you split it into the groups, becomes a product of pseudo posteriors where you put the prior to the power 1 over s. And so if you look at those as posteriors for which you can produce simulations, you are delivering in parallel S samples from these pseudo or sub posterior distributions. And the question is then how to aggregate those different samples to, in our case, return one single evidence that merges correctly the evidence produced by the different subsamples without exploiting the other data sets from the other servers or the other agents. So we are interested in M, that is the integral of the product, and we are given samples that, given the previous part of the talk, could return estimates to the partial evidences, the M tilde of ys. So of course, the integral of the product is not the product of the integrals, but they can be connected by renormalizing the right-hand side, namely that the full evidence is a product of the partial evidences times the normalizing factor to the power s for this inner integral, and times the product, the integral of the product of the pi tilde. So this is a formula that that is available in the paper by Buchholz et al. I just mentioned. Well, this is just what I explained, that the Z is the normalizing constant for this sub prior. Now, while this is a nice formula, we are again hitting the label switching problem, assuming that the model is a mixture, because if we use this numerical approximation to the integral I, the correction factor in the product of the evidences, we are exploiting the missing or latent data structure of the mixture. So where the latent variables are produced by this pi tilde. Unfortunately, the Zs that come from one run for one server have no connection with the Zs that come from another server. And so, in other words, if for all data sets, the modes are located roughly at the same spot, so if all data sets return essentially the same information about the data, for one data set, the Z would be around that mode, and for another one, it would be around this mode. So the meaning of 1, 2, and 3 for the first data set has no connection with the meaning of 1, 2, and 3 for the other. And so if we have label switching in the picture, aggregating the different groups become an issue because we cannot give the same meaning to the Z. And so that was not a point that was considered in the 22 paper, where they were only dealing with unimodal, or essentially unimodal model. And so if you don't pay attention to that, you get very, very poor approximation of the evidence. This is a simulation run by Adrian, where the true number of components is 2, for instance, and you have data that is split into 7 groups. And the true evidence is the red line, and the range of the estimated evidence is quite below. Actually, it's surprisingly, it gets better for more components, but it's because the data is poorly compatible with this number of components, and therefore, along this simulation, there is a lot of fluctuation between the group that reproduces the label switching in the end. So this is less a victim of label switching because it's a poor model. But with the right model, you get a very poor approximation to the evidence. And now, what are the possible solutions? Well, one is, again, to call for averages over all permutations. But then it becomes even more of a challenge, because not only you have to consider the set of permutation once, but S times, or S minus 1 times, to make Z1 and ZS to have a chance to coincide in terms of labeling of the modes. So when it's feasible, it works, but of course it's costly. So this is an illustration of why it works. It's a comparison with or without averaging over the permutations. Yeah, so the cost is quite a challenge. And so the notion is rather to try to move in an informed way the latent variables to make them coincide with those in the first sample. And this returns to some existing strategy in the mixture estimation literature of finding orders that you can refer to. So in papers by G. Solo or Matthew Stevens around 2000, they were running their MCMC and then relabeling so that you bring the points close enough to one reference value. And so this is what we also implemented in this proposal. For each of the group, I mean, there are a lot of notation, but just trying to figure out what is the best allocation in terms of probabilities. So we would make proposal on the permutations themselves to bring the other samples for batch S close to the one for batch 1. And this reduces, of course, the number of simulation because you don't average over all permutations. And nonetheless, this brings, I mean, a computable estimator and performances that are, I mean, not so different from the average over permutation. So this is maybe an unclear illustration where actually this proposal does better than the average across permutation because we take into account the computing time. Okay. And then in this approach as well, we can improve things by doing sequential important sampling, for instance, running through the groups rather than doing it all at once. And this induces a slightly improved, or well, depending on the judgments, rather improved version, again for the same computing cost on the approximation of the evidence, no matter what the number of components. Okay, I have 5 minutes. Yeah, just have 50 slides, so it's fine. So, I mean, to fit with the announced topic of the talk, let's go a little bit over the case of infinite mixtures. So infinite mixtures are, well, mixtures with an infinite number of components that you model in a somewhat non-parametric way or heavily parametric way, depending on the perspective. Namely that you are in a certain group with probability pi k. You may have an infinite number of groups, and the pi k's are driven by a certain distribution with parameter m being a positive real number. And actually the sum of the weight is 1, so you must have a distribution that makes the sum of infinite weight equal to 1. And so one classical choice in the literature is a stick-breaking distribution on the weights, where each weight is a break of the previous one. So you take probabilities nu I, and then this means that you break 0, 1 into 2, and then the second part you break it into 2 again, and you keep multiplying this length, and you get the pi k's. G0 is a prior on the seers, and this object that you return formally writes this way. There are alternative ways to write it in a computable manner. You start with the first one, then the second one given the first one. This is a Chinese restaurant process representation. And I mean, the funny thing is that despite this is rather heavy machinery, the fact that it is non-parametric, infinite, I mean, it's feasible to write the distribution in a closed manner, integrating out the parameters if you condition on the latent variable, assuming that G0, the distribution of theta, is of the same type as the density, so you must have exponential family. And thanks to this closed form representation, there exists as well a Chib's formula for that model that was produced by Bashu and Chib in 2003, but it is slightly ignored in the literature. It's not so well known. I mean, you can repeat what I said previously, thanks to the fact that the P of X given M and G0 is available, because then you can also deliver an unbiased estimator of the posterior distribution of M given X, thanks to the specific choice of this prior. And so, I mean, you can return an approximation that is computable, that again suffers from label switching. And just in the final slide, I want to make another proposal in the same context that uses what's called a reverse logistic regression that is itself slightly overlooked. It's due to Geyer in a non-published technical report, a famous unpublished technical report. And it's connected with noise contrastive estimation, namely that, or the mixture representation I presented earlier, namely that if you are looking for a missing constant, so my missing constant is M of Y here, and if I can produce a sample from an alternative distribution where I know the constant, so let's call it pi 1 on Z and the label capital M. So if I have samples from both distributions, in the second case, I don't need to know M of Y for producing another sample. Then the incredible trick of Geyer is that the log MY is the intercept of a logistic regression of the two samples. When you use as a regressor the log of this ratio, by 2 tilde being the top set. And this method converges, it is asymptotically equivalent to bridge sampling, and well, it is the basis as well of NCE. And if I can show this one final picture, in that non-parametric case or infinite dimension case, when using the prior as the alternative distribution, you don't get a very efficient approximation to the evidence. But if we use this pseudo posterior as the alternative proposal, where we can compute everything at fixed computing cost, we are doing better than the cheap solution. Even though the comparison is not so exciting as in early case. Okay, that's it. Again, thanks a lot for the invitation, for being here, and thank you for listening to me.
Thank you, Christian. Do we have some questions for the speaker? Nobody? All right, I can ask a few, it's my field. So one question was on the sequential importance sampling when you split the data into capital S sets. So if you do that sequentially, won't you get an exponential variance in terms of capital S? And I guess the idea is you want to make S relatively big for large data sets, is that correct?
Well, the S is never that big.
Okay.
So we don't have to do many steps. It's just that we had at fixed computing cost, we are doing better by reordering one at a time rather than all together.
Okay.
So using the merge sample provides some stabilization. When the merge sample in without seeing them, just creating the object. So we don't see the exponential explosion.
Okay, all right. And the second question, so when you use SMC, you can obviously get an unbiased estimator of the marginal likelihood for a given K. And so there was this very nice proposal of Christophe Andrieux and one of his PhD students a long time ago to use this for essentially particle MCMC to do a reversible jump. I was wondering what you thought of this idea, because you did say earlier that adaptive SMC fails, which it's a question.
Yeah, I don't remember this paper by Christophe.
With Karniadakis in JCGS, I forget the year.
Okay, so in the 1990s, no?
No, after 2010,
okay.
Yeah, it was a PMCMC method.
No, I don't have an answer, right? I would have to reconsider that.
Yeah, because the acceptance rates were pretty good. So instead of doing like the split and merge, which we know is kind of, as you know better than me, this was destined to fail. This was working quite well because you were using the SMC to, once you'd moved the dimension, to kind of temper and get a better kind of feel for what the target looks in the new dimensional space. So it was kind of
it
nice.
makes sense.
Yeah. We can discuss it afterwards.
We can think about it.
Yeah. Interesting. Yeah. If there are no other questions, let's thank Christian once again. Thank you very much for your talk. So I think that's it for today. Thank you.